Welcome to CS350. This is Karthik Gopalan. In this lecture, we will look at the topic of segmentation under memory management subsystem. So normally, every process has a single address space, which ranges from 0 to a maximum value of the virtual address. Some part of the address space may be dedicated to data, some part may be dedicated to code. What if a single process could have multiple virtual address spaces? So in this case, you could put code in one virtual address space and data in a separate virtual address space instead of having them share the same address space. This could give you some security benefits. For example, if someone injects malicious code as form of data, then that would be separated in a data space that will never be executed. So there are also other possible uses. For example, let's take a compiler program that has a lot of different data structures. You might have a symbol table, the source code, constants, parse tree, call stack, and so on. Normally, all of these data structures would have to share a common address space. But if this compiler program used multiple address spaces or multiple segments, then each data structure could be assigned its own segment, and every segment can grow and shrink independently of others. So data structures that need lots of space would have large segments, and data structures that need less space would have small segments. So there are basically two techniques that are orthogonal to each other: paging and segmentation, and each of them has its own benefits. So note that paging and segmentation don't have to be exclusive to each other. But we need to understand the specific purpose of each technique. So when you're using paging, the primary purpose of paging is to allow the amount of memory used by programs to exceed the total memory capacity of the physical machine. On the other hand, with segmentations, the primary purpose is to divide up the contents of a program into multiple logical segments, each distinct from the other. So as a result, when you're using paging, the programmer doesn't need to be aware of the fact that the address space is divided into pages. The operating system automatically creates pages and swaps them, pages in and pages them out from the main memory. With segmentation, however, the programmer has to be explicitly aware of the presence of segments so that the different data pieces can be addressed appropriately. With paging, as conventionally used, there is only one address space, whereas with paging, there may be multiple address spaces, so one associated with each segment. So with both techniques, the total address space can exceed the size of the physical memory. So let's consider pure segmentation where we do not perform any paging. In this case, every segment is either kept entirely in the main memory or it's not kept in the main memory. Perhaps it's kept on the disk. If we do this, then note that every segment can have different length. Different segments can be of different sizes. This leads to a unique problem called external fragmentation. As an example, consider 4 segments that are stored in the main memory at a certain point. Each segment is a different size. At some point, we evict segment 1 and bring in segment 7 into the main memory. Segment 7 is a little shorter than segment 1, so this leaves about 3 kilobytes of free memory in the main memory address space. At a later time, we evict segment 4 and bring in segment 5. This leaves another hole in the main memory, which is basically free memory at another location. Over time, as you bring in and bring out segments, the entire main memory will have different slots of different sizes that are free and not allocated to any segment. This is known as a checkerboarding pattern, where essentially you have free memory but they're distributed at different locations in the main memory. So let's say that in figure D, you had to bring in a segment whose size is greater than 4 kilobytes, maybe like 5 kilobytes or 6 kilobytes or so on. Although there is sufficient free memory available, but it's not all in one place. So you cannot bring in a segment larger than 4 kilobytes. So in order to enable a segment larger than 4K to come in, we have to do something called compaction. Compaction means that you move all the used segments to one end of the physical memory so that rest of the free memory is available for larger segments. Now you might notice that this technique is similar to another technique called defragmentation that's used on the disks. Sometimes on certain operating systems, you may perform defragmentation to move all the used files to one end of the disk so that there is enough free space available at enough contiguous free space available in another end of the disk. So compaction is very expensive because it involves physically copying data from one part of the main memory to another. So you don't want to do compaction very often, but periodic compaction can increase the amount of contiguous memory that's free. So we will first consider the earliest segmentation architecture, which was introduced in the Multics operating system. Multics operating system ran on one of the IBM mainframe systems, and it was a pioneer of sorts in introducing the modern segmentation architecture. So under Multics, every process can have multiple virtual address spaces or multiple segments. Each segment was paged, meaning that every segment could be broken up into pages, and the pages could be paged in or paged out, moved in and out of the main memory as needed. As a result, every segment had its own page table. So you have a situation where a single process has multiple address spaces or multiple segments, and every segment has a separate page table. So in the previous discussion, we had learned that every process is a single page table, but now we see that under Multics, if a process had multiple address spaces, it can have multiple page tables, one for each address space. So the advantage here was that every segment could have the full virtual address space allowed by the architecture, allowed by the number of bits in the address allowed by the architecture. However, disadvantage was that if a process was accessing data from multiple segments, then switching the MMU context from one segment to another involved changing the page table base register to point to a new page table. So even though the process is not performing a context switch, the CPU is not being context switched, you have to perform kind of a mini context switch on the memory context. So this could have significant performance impact if it turns out that there is only one TLB and the TLB has to be flushed every time you switch from one segment to another. So let's take a look at how address translation worked in Multics. The Multics virtual address consisted of two parts. There was a segment number which identified the specific address space being accessed, and then there was the actual virtual address within the segment. The virtual address consisted of a page number and the offset. So the MMU would first look at the segment number and access a segment descriptor table. So the segment descriptor table had one entry for each segment. This entry was known as a segment descriptor. So you would use the segment number as an index into the segment descriptor table, access the specific descriptor for the segment you are accessing. That descriptor would give you the address of the page table for that segment. So using the address of the page table and the virtual address, the page number, you would then find the specific physical page frame that you're trying to access, and from the physical page frame you would then use the offset to access the specific byte you are trying to access. There's a segment lookup from the segment descriptor table, then a page lookup using the page table, and finally accessing the byte. So, here are some lower level details. You have, as we discussed in the previous slide, the segment descriptor described each segment, but it also gave you the base address of the page table for the segment. The segment descriptor format is also shown. You don't have to memorize it, but it's worth taking a look at the various fields to get a sense of what information is there in a segment descriptor. So besides the memory address of the page table, you could, in Multics, you could specify various segment lengths in terms of number of pages. You could specify the page size. You could also choose whether the segment was paged or not paged. In addition, there were some protection bits that would specify whether a segment is read-only, read-write, who can access the segment, and so forth. In modern systems, segmentation has been adapted to meet the needs of modern applications. So in this slide, we are talking about the Pentium architecture, which borrowed many ideas of paged segmentation from Multics. However, there were significant differences. Now, the main problem with Multics was that since each segment had its own page table, switching the memory context from one segment to another could have been expensive. So with Pentium architecture, a process can still have multiple segments, but all the segments map to a common linear address space. Every segment is defined by a base and a limit. So the base is a base address in the linear address space of the process, and limit is the maximum address that a segment can access in the linear address space. So, instead of having multiple separate virtual address spaces, we have one linear address space, and multiple segments share this linear address space. In this picture, we have three segments, each with its own base and limit, sharing the linear address space. Also note that different segments could overlap with each other. For example, limit of one segment could exceed the base of another segment. So given a linear address space, there is a single page table that maps the addresses in the linear address space to the physical main memory. So now we solve the problem of having multiple page tables for a single process. A process has only a single page table, and every segment has a base and limit that maps it to the linear address space. So how does the memory address translation work in Pentium? Just like with Multics, a virtual address consists of a segment selector and an offset. The segment selector gives you the index into the segment descriptor table, from where you extract the segment descriptor. Segment descriptor has the base address of the segment, limit, and additional fields such as protection bits. In addition, there is an offset which is added to the base address to derive the 32-bit linear address in the linear address space of the process. So first you convert the virtual address to a 32-bit linear address by adding the offset to the base address of the segment. And then you use the page table of the process to convert the 32-bit linear address into the physical address. So the second step in this process, converting linear address to physical address, is exactly the same as what we learned earlier about converting physical addresses to linear addresses using page tables. So you first look up a page directory using the first 10 bits of the address, and then you look up the page table using the next 10 bits, and finally the specific byte using the offset. So as we can see now, there are two steps for looking about converting a virtual address instead of one step. So first step is converting the virtual address to a linear address. The second step is converting the linear address into a physical address. So this slide gives you a little bit of low-level details about what the Pentium selector looks like and the specific format of the segment descriptor. Again, it's worth looking at certain fields to understand what information is contained there. So if you look at the Pentium selector, you will find that there is a bit that indicates whether the descriptor is a global segment or a local segment. Global segments are segments that are used throughout the operating system. So a global segment is applicable to all processes in the system, whereas a local segment is specific to a specific process. So the GDT LDT bit indicates whether it is a process specific segment or a system wide segment. In addition, there are a couple of bits that indicate the privilege level of the segment. It shows who owns the segment, whether the operating system or user level processes, and who can access these segments. In Intel, there are four privilege levels: 0, 1, 2, and 3. 0 is where the operating system runs, and 3 is where user level applications run, and 1 and 2 are normally unused. So the segment descriptor table looks complicated, but essentially it has a base address of the segment and the limit. Plus, there is the descriptor privilege level, 0 to 3, and additionally, there is a bit which indicates whether the segment is present in the main memory or absent from the main memory. Here are some additional references that you can look up to learn more about segments and specifically how x86 architecture handles segments.